represent the equations of motion by graphical method. Earlier, we have studied the motion of an object along a straight line in uniform velocity. Now, let us see how the velocity, acceleration during motion, and distance travelled by an object during a certain time interval can be related using a set equations called as equations of motion. The three equations of motion are v is equal to u plus at, s is equal to ut plus 1 upon 2 at square, 2as is equal to v square minus u square, where u is initial velocity, v is final velocity, s is the distance travelled, a is the uniform acceleration, t is time. The first equation, v is equal to u plus at, shows the velocity-time relation. The second equation, s is equal to ut plus 1 upon 2 at square, shows the position-time relation. The third equation, 2as is equal to v square minus u square, shows the relation between position and velocity. Now, let's see how we can derive these equations of motion by graphical method. Let us start with the first equation, equation for velocity-time relation. Consider this velocity-time graph, where time is taken along x-axis and velocity is taken along y-axis. According to this graph, the object starts at point A with an initial velocity of u and moves with an uniform acceleration. And the final velocity is v, marked at point B in time t. Let the change in velocity at a uniform rate be a. Draw two perpendicular lines BC and BE from point B to x-axis and y-axis respectively. Now, OA is initial velocity, BC is final velocity, and OC is time interval t. The change in velocity is shown by the line BD, where BD is equal to BC minus CD. Now, let's draw a line AD parallel to OC. We can see from the graph BC is equal to BD plus DC is equal to BD plus OA. Now, we can substitute the value of BC and OA in the previous equation to get V is equal to BD plus U. BD is equal to V minus U. From the graph, we can find the acceleration A is equal to change in velocity upon time taken, which is equal to BD upon AD, which is equal to BD upon OC. Substituting OC by T, we get A is equal to BD upon T. BD is equal to AT. By substituting the value of BD is equal to AT in BD is equal to V minus U, we get V is equal to U plus AT. Now, let's derive the second equation, equation for position-time relation. Let us say that a car has travelled a distance s with a uniform acceleration of a in time t. The distance travelled by the car can be obtained from the enclosed area OABC in the graph. Let the distance travelled by the car be s, which can be calculated as S is equal to area of OABC, which is equal to area of rectangle OADC plus area of triangle ABD, which is equal to OA multiplied by OC plus 1/2 multiplied by AD multiplied by BD. By substituting OA is equal to U, OC is equal to AD is equal to T and BD is equal to AT, we get S is equal to U multiplied by T plus 1/2 multiplied by T multiplied by AT, which is equal to UT plus 1/2 AT square. Now let's move to the third equation, the equation for position-velocity relation. In the previous equation for velocity-time relation, we saw distance S is equal to area of the trapezium OABC. Now, by applying the formula for the area of trapezium, we get S is equal to OA plus BC upon 2 multiplied by OC. By substituting the value of OA is equal to U, BC is equal to V and OC is equal to T, we get S is equal to U plus V upon 2 multiplied by T. From the velocity-time relation, we know T is equal to V minus U upon A. By using the value of T, we can write the distance as S is equal to V plus U upon 2 multiplied by V minus U upon A, which is equal to U plus V multiplied by V minus U upon 2A, which is equal to V square minus U square upon 2A. 2AS is equal to V square minus U square.